So checking our homework. Number 2, the answer should have been calculus is required. The reason, velocity is not constant. And how did you know that? What they give you for velocity? They gave you a function, exactly. If velocity is constant, question kiddos, what are they going to make velocity equal to? One number, right? One number. If velocity is constant, they're going to make it equal to one number. Okay, moving on. You guys can already see number 4, right? Did you have to solve number 2?
It said asked you to estimate.
Okay. There were multiple ways of estimating. Can you tell the way that the book did it? It's not necessarily the only way. But how did the book do it? What velocity did it choose? Which velocity did it choose?
The constant part of the function.
Yeah, and I think also when time was 0. Is that what it was? Look at your function real quick. You should have written it down because it was part of the problem.
20 plus 7 cosine 15.
Okay, so if you plugged in 0, it would have been 21. Because cosine of 0 is 1. That'd be 27?
It was 26.761.
Oh, was at t equals 0. Okay. So you could have done just one velocity. So you could have chosen the velocity at 0 and multiplied by 15 seconds. What was the velocity at 15? 14.6. You could have used 14.6. Or you could have actually done kind of what we do with rectangles. I'm not going to go too much in depth in this, but you could have done where you split up the interval into sections. And so if you think about it, you would have had between 0 and 15. And theoretically, you would have had this velocity graph. You could have thought, what if I were to go from like 0 to 5, and then from like 5 to 10, and then from like 10 to 15? Pretend that's even. It's closer. So you could have thought about splitting it up and saying, hey, let's think about 0 to 5. So I could do like velocity at 0, so that'd be rate, times time, that'd be 5 seconds. Then you could have done like velocity at 5 times 5 seconds. Then you could have done velocity at 10 times 5 seconds. You could have said, hey, I'm going to use this velocity for a little bit, this velocity for a little bit, this velocity for a little bit. You might see how area actually corresponds to finding the distance given velocity. It's kind of interesting. It's kind of weird and out there. We'll talk about it second semester. But you could have also tried to make it more precise by splitting that 15 seconds into smaller intervals, and you would have gotten a closer approximation. They went ahead and just kind of stole the velocity from number 1. And the reason they did that, what was that, number 2? They just stole the constant, kind of like Sean said. So he was like, when cosine is 0, the velocity is going to be 20. So you kind of stole the constant part, ignored the variable part, and we're like, well, let's approximate with that. So was it unapproximate? The answer is yes. Was it a great approximate? The answer is no, and here's the reason why. Because if you wanted to figure out what this would be exactly, you guys want to see what the exact answer would be, just because you had to approximate last night? If you want, you can grab out your calculators. Didn't I just say this kind of had to do with area? Do you remember which calculator function? I barely introduced it yesterday. Which calculator function helps us with area?
Weird integral thing.
The integral thing, the little SE symbol that is an integral. I may as well use the correct terminology even though we haven't taught it. Remember we did this yesterday using second trace and using the integral? We could do that with our function. Our function is going to be the 20 plus 7 cosine t. We might want to do zoom fit. In calculus, we're always in radian mode, always, always, unless you want to visualize with degrees, but you're going to change them back to radians. I'm going to do zoom fit. Is that zoom 0? 8? Is 8? Okay, now I don't trust you. I heard like 3 different answers. Zoom 0, okay. So, and then we're supposed to do it for 15 seconds, right? So I'm going to go ahead and make my x, which is like t, and then make sure I go to 15. Okay. There is a little dilemma with this. Do you guys see how I think it goes below the x-axis? Let's go ahead and make sure our y goes negative. Oh, maybe it doesn't. I want to see my axis. Okay, it doesn't. If this went negative, I'd be in super big trouble. And we'll talk about that second semester with how total distance traveled. You don't consider changes of position being positive or negative. They have to always be positive. I'd have to put an absolute value in. Don't stress about what I just said. Just think, this is all positive, so that's good. And then we're going to do second trace. We're going to do an integral. What do you think our lower limit would be? 0, because the first 15 seconds start at 0. What's the upper limit going to be? 15. What would the actual be?
Boom.
304. Ooh. So 300 is not that bad of an approximation.
Where's the,
And if you think about it, if, what was I asking you guys? 26 or 27-ish was the velocity at 0. That's how high it goes. How low it goes, you could have plugged in, technically, cosine is -1 at pi. So you could have plugged in pi. 20 minus 7 would be 13. So if the high is 27-ish, if the low is 13, you could find the average and it would be about 20. So what they did, another way of thinking about it, is they found the average speed and they just kind of used that, which ended up being not too bad in approximation. 15, because the first 15 seconds. Alright, I talked about that one a little more than I intended to, but there is a lot of calculus involved. And they had you approximate, so I wanted you to be able to compare to the actual, just to see how close you were. Number 4, the next one. Answer should have been pre-cal, no big deal, find the slope, rise over run. But the nice thing is they gave you the equation. All you had to do was pull out that n equals 0.08. Number 6, was that a calculus or a non-calculus? Oh yeah, that's not a geometric shape, there's a curvy side, right? So, calculus, how did you guys estimate? Who made a rectangle? At least one. Who made 2 rectangles? You did. But how did you guys estimate that?
I cut it up.
Use a graphical or numerical approach to estimate the solution. You had to estimate somehow. So you could have made the base, what, 2, and the height, I don't know. Could have gone halfway between 3 and 1 if you wanted. Made the height 2 and then like 2 by 2, make it approximately 4. Could have done that. You could have split it up and been super snazzy like we did in class yesterday with maybe more rectangles. But either way, an approximation. Their approximation was just the 2 times, so they did 2.5. So they got 5 square units. I just chose the halfway in between 3 and 1. Could have been 4 square units. It was an approximation, kiddos. You did not have to do it necessarily exactly how they did. But long story short, it did need calculus, and you had to use some sort of geometric shape to kind of approximate what you thought that area might be. Number 8, pre-cal, no big dealio. Plug it into. Yeah, you kind of had to plug it into distance formula to figure out what the radius was. End of the day, distance formula between -2, 1 and -1, 0. Your radius ends up being √2, and then you just have to plug into the area of the circle, pi r squared. So you could have done that one precisely and gotten 2 pi. That's actually really similar to one of the first pre-cal problems in your first homework last year. Having to find the distance to find the radius and then plug and chug. And then you guys had number 10 also. How'd you guys do number 10? Before we go look at it, so right now it's not showing. Pre-cal or cal?
I said pre-cal. Even though it's probably calculus.
Depends how you look at it. Probably calculus because there is a curve, but why could you kind of say that you could get a stinking close approximation with pre-cal?
Because it's a
Because
square.
it looks like a square. So then how'd you guys find the area? 1 times 1. Careful, the units were 0.5. So it was 0.5 on one side, 0.5 on the other, so 1 by 1. You might have accidentally thought it was 2 by 2, but if you look at the units, the tick marks, it was half, half, and then a whole. So it was 1 by 1. So the approximation would be 1. I would have said calculus because it is curved, and they say calculus as well, but you can say, well, pre-cal got me a stinking close approximation. Maybe even basically a precise approximation. Okay, the next even was, I lost track. We had 1 through 10, and then we had 18, and then 22? Okay. Number 18, you guys were doing what we did yesterday, true? We had to do it twice? Now, hold on. Did they show very much work? Or is this just what they plugged into their calculator? It's just what they plugged into their calculator. So can I have someone help me, just because this was one of the homework questions up on the board, can I have someone, just for sake of time, read off what they set up before they got to this step, if you did show your work, and if you did flesh it out a little bit. What was there before this part right here for area in number 18? I think the first one was under, right? Oh, we could just say 4 rectangles. So you could say when n equals 4, right? And then the next one was n equals 6.
We had multiply all the base and heights, but it was basically 5 over 4, all. Yeah.
Good. I'm just showing. Pi over 4 were all the bases. How'd you get that name?
Because it was 0 to pi, divided that by 4.
Remember what we did yesterday for our delta x or for our base? You do b minus a all over n. Okay, so all the bases were pi over 4. And then what did you do for all of the heights?
But then you had you have to plug it into your rectangles, your x values into the function.
And was it sine?
It was sine.
Okay. So automatically, without even thinking, I know I'm plugging into sine, but what am I plugging in? How did you use the picture to help? Or what did you end up using to plug in? Yeah, unit circle. And according to the tick marks, did you guys realize the tick marks were half of pi over 2, so pi over 4? So if you go to the height of the rectangle, hopefully you have it in your homework, so you can actually look at this, but really quickly. Here's pi over 2, there's 3 pi over 4, there's 1 pi over 4. If you look at the first rectangle, where does the first rectangle, approximately hit the curve? It hits the curve at pi over 4. So I say, oh sweet, I just want the height at pi over 4. And then where did the second rectangle hit the curve? At pi over 2, so I plug in pi over 2. Where did the third rectangle hit the curve? It hit the curve approximately at 3 pi over 4. So I need the height at 3 pi over 4. And then last but not least, wait, there wasn't one. This is tricky. We saw it yesterday. What happens if the height is 0 at a value?
You give up in the
No. It's just going to have, 0, which would be the same. But you still plug in the value just like you were doing, but what's this area going to end up equaling to? 0. Which is why when you look up there, there is no fourth rectangle to end up being 0. So what did they do? Guys, couldn't you have plugged in this plus this plus this plus that in your calculator and have the right answer? Yeah. But what did they use to simplify things? Because they're like, we know unit circle. Root 2 over 2, 1. Root 2 over 2, 0. Where? Oh. So, at the end of the day, your area ended up being. For 6, I'm not going to do the entire thing, but what's going to change with your areas? You're going to have A1 all the way through A6, right? Not that kind. What's my base going to be of them? Pi over 6, because if you look at, you would have had to probably look at the tick marks because the rectangles were confusing, only 5 were shown. If you look at the tick marks, pi over 2 was cut into thirds. That's pi over 6. 1 pi over 6. That's going to be my basis, b minus a cut into 6. And then still going to be plugging into sine. I'm going to do the first 2 just for sake of illustration real quick. Where did the first rectangle hit? At pi over 6. Where did the second rectangle hit? How do you count units? 2 pi over 6, because there were 2 units, but what is 2 over 6 reduced to? Pi over 10. And then you would end up, once again, at pi. Then you can plug and chug it, you have your answer, sure? Okay, I know it was true, I know it wasn't quite true, but was it possible? And the answer was yes. How many rectangles are shown here? 5. But why were there 6?
because
Sine
one's
and
at
pi is-
0.
Okay. And then we had 22 and not 24, right? Just 22. So let's go peek at number 22. I think he's over here somewhere. There he is. A. Can anyone talk through, this one was kind of out there a little bit, right? Can you guys talk through how they figured out A, if they had it right? Sean.
Well, I just looked at it graphically, like I copied down the graph and then I just plotted.
Yeah, plotted the different lines and said which one, wait, how do you know which one's the tangent line? What does the tangent line look like on a graph at a point?
It's only at like that.
It skims, right? It goes through the point and it skims the graph. So if you look at your parabola, you should have it, well, in the future, you'll have this picture in your homework. You don't have to get out your book and look at it. Just look at your homework. The picture's right there. You would have all the different option choices. You'd circle the right one. Only that one curve, the one that has a y-intercept of -5 and has a positive slope of 2. Well, first of all, why did we cross out letter B and C, both of them with negative slopes? Why does that not make sense if this is my point? When you skim, it has to be going uphill right there, right? That's uphill. That's a positive slope. The negative slopes would be on this side. So right away, it's not B or D. I have a 50% chance of getting it right. And if you just figure out, it's much steeper than 1/2. Well, all right, so we've gone ahead and gone over the evens. That's 18 and 22 of our question list that was done. We have questions on 3, 9, and 13. I'm peeking at them really fast to see what verbal explanation is needed. Number 3 says a path is modeled by a function. They show us a picture. They want the rate of change. What did I say yesterday we should think of as a synonym to rate of change? Slope. So look at the path. In the future, you'll have it on your paper, right? Because we'll sketch it out. If you look at the path, it's going to be a downwards parabola. Okay? And x equals 2 hits right about, if I was to do this, right about here. Okay? Question. How do I find the slope of a curve at a point? It's going to be a tangent line. As soon as you say tangent line, I'll say calculus. Why? You have one point, and it's a curve. That's calculus. If it was a line, could I find the slope of the line at a point? Yeah, if it was a line, I'd say pre-calculus, and we just do lines over lines. But since it's a curve, and since I need the slope of the tangent line at one point, it's calculus. And does it say to approximate? It does say to approximate at 2, I don't know. Up 1, over, it's less than that. Up a half, over 1. Maybe a slope of a half, maybe a slope of a third, some sort of really small slope. Some sort of really small slope, because that is not sloped very steeply at all. We could say about 0, it's almost 0. It is sloped up, but it'd be flat. You could do like 1/5, 1/10, I don't know, some sort of fraction saying it's a very small slope. That was number 3. Number 9. Oh, it's pre-cal all the way. You could make it like a square and a square, and you actually make it one big old rectangle and 2 little triangles if you want to be snazzy. Or you could have made it 2 different trapezoids. That would have worked too. Because as I look at my figuring, guys, I'm just showing you how to do it. You would have to figure out the measurements, I have full head, figure out the sides. Couldn't you have done a rectangle for all of this?
Yeah.
And then done a triangle for that? So I would have done base times height plus 1/2 base times height. You just have to count 2 times. That's what I would have done. And last but not least, we have number 13. And number 13 was just like our class activity from 2 days ago, our group exploration. In that, it gives you a function, and it gives you points, and it asks you for secant lines. So long story short, on number 13, I believe it gives you. You guys help me out with the information, those of you that need to write down the problem. Where's the point of tangency it's talking about for square root of x?
4/2.
So this is ultimately like my point P from our activity the other day. This is 4/2. It asks us, I believe, about point 1, and at 3,
And then 5.
and at 5. Stop joking. Long story short, if you go to 1, go to the point, couldn't you make a secant line by just connecting those two? Isn't that straight? At 3, you can make another secant line. And then at 5, couldn't you make another secant line? So you have one secant line there-ish, you have one secant line there-ish, and you have one secant line there-ish. There you go, there's the 3 lines. All kind of centered around this point right here. So what were you supposed to find? I know, I have a marker. Calm down. You were supposed to find slopes. How do you find slopes? Just what you did in your workspace 2 days ago on the group exploration, right? If I have the point 4,2, if I'm doing the slope when x equals 1, if I'm doing the slope for x equals 3 between a point and the point of tangency, I'm just going to do one of them, 5 of them. I'm going to do one of them. For this one, you would do f of 1 minus f of 4, all over 1 minus 4, because we're using this guy right here. So you would plug in who is the x value, and you guys were right, it is going to end up being square root of 1 minus square root of 4, all over 1 minus 4. I have my slope of this line. My slope is going to end up being 1. I'm going to double check. Because 1 minus 2, oh, negative 1, sorry. I didn't take the square root of 4. Negative 1/3. Negative 1 over negative 3 constant. I did square root of 4. It's going to be 1 minus 2, which is negative 1, and 1 minus 4 is negative 3. So negative 1 over negative 3 is 1/3. Do the exact same procedure with 3 and with 5. Question: were the group explorations meant to help with homework? Was it all of them? Did I cover every single topic covered in section 1? Yeah. Most of them. In tons of detail? No. Why? Because it's a preview. All right, cool kids. Notes out. I went over lots more than I usually do because this was a weird section and there was a lot of math that you only got a preview to, right? And that's hard in math. When you only get a preview and have to do homework, that's hard. So that's why we did the group exploration. That's why we actually worked out in finding slopes on group exploration 1. Finding areas, group exploration 2. There was a point, there was a purpose. Please help it encourage you guys to stay focused in class. We're going to go ahead and start section 1.2, which you guys will enjoy because we get to get kind of back to a normal lesson.
Yay.
Meaning, I'm not previewing the entire year of what we're doing.
Yay.
And trying to refer to ways it's going to be applied, etc. Section 2 is all about, you guys look on the backboard, limits. But I'm doing limits graphically and numerically. Graphically is pretty obvious, it's using a graph. Numerically, sorry, computer's super slow. Numerically, well, that's using a table. But as we saw from all of the work that we did with the group explorations in the tangent line problem and in the area problem, with pre-cal we can approximate to make the jump to the actual answers to those problems. We need limits, so we're going to finish off chapter 1 talking about reviewing me teaching, even though you guys already got introduced to it in your summer packet and last year. We're going back to the beginning of limits. They're so stinking important, because they form the foundation for our entire year. The idea of infinitesimals, aka super small values that we can still call values. I should say infinitely small values that we still see as an actual value. Made the way possible, basically, for all of calculus. That is what both Newton and Leibniz had to figure out, the idea of infinitesimals. Now remember, if I said this last year, you guys are writing, that's totally fine. You don't really need to skip any space anywhere. I just did it to make it look nice. Yeah, remember it's the complicated definition, no, not the super complicated one. I think go with the epsilon delta definition. If you ever take a calc class in college, don't refer to the epsilon delta because there's probably some sort of mathematician that loves all the proving and all the behind the scenes and all the reasons as to why everything is the way it is. You can read the epsilon delta definition. If you want a college level approach, a college level description of a limit. In section 1.2, it is there. I'm just not going to take time on it because it is not a skill that I desire you to have. And basically, my approach this year in calculus is to give you the skills as to how to do calculus, whereas some college professors would rather you know the theory behind where the skills come from. Two different approaches, depends on the professor you take, whether they're applied or pure, as to which one they're going to focus on. Obviously, you know from the outset, my focus is the skills. Yes, for the AP, but we can put beyond. As you guys write this, we have officially gotten in the calculus and in the calculus notes. As a result of that, I'm going to go ahead and give you guys a calculus letter from last year. Yes, I have read all of theirs, and I have actually scanned all of the letters from last year, A, B, and B, C. If you guys do want to go check out more. They're not in alphabetical order. Well, BC is, but ABO is too lazy to do it. So you have to actually scroll through and find your friends or whatnot who took it last year. But if you guys look in your shared folder, there is letters of advice. I sadly started doing this much later than I would have hoped. I didn't realize we had a scanning capability, and so it just was kind of impossible for a few years. But I did start 2 years ago scanning the letters of advice in. So you guys, if you want to go read more, you can. They're all up there to read. But you have your special one. Please take their advice to heart. I did not tell them what to say. All I did is give them this form, and if you guys read it, what's it say?
Write a
letter. Sharing helpful advice. Who are just starting this journey. What worked well? Is there anything you wish you had done differently? What carried you through the more difficult sections? Some people do joke about dropping the class, and some actually challenge you and say, if you're not willing to put in the work, why are you here? I read a few letters like that. Quite a few, actually. So yeah, as specific as you'd like, keep in mind I'll be reading your advice. Every now and then there were random kids who also, I think it was mostly BC, but they just were giving their numbers out. Like, don't worry, just call. You need to talk it through. It was really cute. But anyway. This one I'm just going to throw away because it doesn't even have a name on it. I don't have any worthwhile advice. Just don't procrastinate and don't think that you can't do it. Persevere through the class. It's actually good advice. They could have actually done a few more sentences and made that a good letter. Who knows who it was?
You threw it away.
There's no name on it. I read it to you. You heard it. All right, cool kids. Let's go back to limits and let's get some stuff done today, even though we only have about 10 minutes. Limits. You've been here. You've done that. You've done this. At least a little bit. You heard, those of you that had me or Mr. J last year, you heard our introduction to limits. In the summer assignment through the website, those videos I had you watch, you heard a very different, a very visual introduction to limits. But the long story short, what I need you to get from this page is, look here at the very bottom. This is the notation of a limit. The rest of it is just kind of fleshing it out and describing it. With a limit, what is new? What is different? This little arrow. The little arrow means. So what we're trying to figure out, and this is actually a huge jump, the equals. The limit as x approaches a. So we have x approaching a usually from both sides, which is what it says up here, from either side. It has to work from either side, meaning from both sides. As x approaches a, we're looking to the y's, we're looking to the heights, and we're asking, can we see where it's going, where it's approaching, not where it is, where it's approaching. And if we can say equals. Even though we haven't gotten there, even though we're just approaching, we can say equals out. So once again, the answer to a limit is what or where the y's are approaching. You guys don't have to write these down. I'm not sure if Mr. Chase showed these last year. I like just showing you a few different ideas as to where limits come into play. In fractals, you can think about the perimeter is actually going to be infinite, which is interesting, but if you think about it, it is contained in a finite space. If you're looking at different artists like M.C. Escher, and if you notice, I have a lot of his pictures up on the wall because he was super cool in lots of different ways as far as his mathematical study and understanding and where it led in his creativity and his art. But he had the idea of limits in the sense that if you can see the little fishes, it's kind of hard for some people to see. Little fishes, they're bigger, and then he's cutting them down proportionally into smaller and smaller and smaller, and as he makes them smaller and smaller, how many more fishes is he fitting in? More and more and more and more. And this is the idea of as they get smaller and smaller and smaller and smaller and smaller and smaller, this process goes on forever. If you can think about it, the number of fishes are approaching infinity as they divide, but still contained within a finite space. There's still a limit, even though there are infinitely many fishes. So you can think about that with our steps in the sense of, and even with, the decimal point. Is there a typo still in that, or did I change it? There's still a typo.
Just trying to get that MC Escher drawing.
There's more up here. Oh, that's more fractals. There's more fishes. That's sinusoidal curves. That's infinitely, but it's actually approaching 0, which is interesting with the butterflies. That's also approaching 0 at the end, and that one's more like fractals in the middle. But anyway, coming back. The repeating decimal, there is a limit, even though you're continually adding more and more digits. This is 0.1 plus 6 hundredths plus 6 thousandths plus 6 10,000ths plus 6 100,000ths plus 6. This is an infinite addition problem, but it's contained in a finite value. Anyway, all ideas with limits. Numerically, tables. You can do this in your calculator as you guys write. I'm going to tell you over here what you would need to change in your calculator to be able to show this table. You have to go to this should be table 7. You make y1 equal to f of x. After you put f of x, the function in the limit, into the y1, go to second window and make your independent. Make it ask. If you follow these buttons, you will see this and you can change it to ask. And then you are able to, in your table, think about you remember from last year, those of you guys that had me, why do I put a question mark for -1 and I don't actually fill it in even if there is an answer? It's the at. It's the end. Do I care about the end or the approach? I care about the approach. So I don't truly, at this level, getting the understanding down of what a limit is. I don't truly care what is happening at -1 if I'm answering a limit problem. I just care about the approach. Now, how can I approach -1 from below? I could do -8, but then I can get way closer with -0.99 and way closer with -0.999. And how could I get even closer?
Well, just keep adding them.
Oh, it's a negative number. Question, is that actually below -1 on the number line? No. So, I need to think about -1. I need to think about -2. Sometimes, especially with negative numbers, I'm trying to point out to you a common mistake. If you're coming from below -1 and above -1, it's going to be a little different than you're used to with positive numbers because these should have been on the other side. -0.8 is less negative, so it's a bigger number. -0.99, -0.999. Now they're closer to the origin, but still a bigger number as far as more on the right. Over here, I could do -1.1, -1.001, -1.0001. Are my x's approaching -1, yes or no? Yes. But as my x's are approaching -1, rain sauce. I'm going to throw it in my calculator really quickly. I froze the screen so that you guys can keep taking those notes. People, if you're watching the video because you missed, you can pause it. Let me go ahead and model what I'm doing for those of you guys that see what I wrote but don't quite understand because we haven't done it before. In my y equals, I am putting my function. Super nifty alpha y equals makes a pretty fraction so we don't mess things up. We have x squared minus 2x minus 3 all over x plus 1. As long as you have it in a fraction, it understands your denominator just fine. I said after you put it in y1, the function, go to second window, independent, make it ask, like I have it right here. Go to second graph where the table is located. You can delete out whatever else you have. But I can type in my -1.1. I can type in my -1.001. Now guys, are these magical numbers? Could you have approached a different way, like -1.002? Would that still have accomplished the same task? Yeah. So I'm just giving you some examples of what I probably would have done. Wait. I did not type in, oh. Remember, there's only so much space to show what value is there. Did I type in -1? The answer is no. So is this plugging in -1? And the answer is no. Did it actually get out -4? And the answer is no. Be careful. Calculator has to round to some degree because there's only so much space for it to show. Now if I was to come from the other direction, I kind of set it up and that's why it's a little bit nicer because I can do my -0.999. I can do my -0.99. I can do my -0.8 or 0.9 or point whatever you want to use. What's going on as I come from this direction? What's it seem to be approaching? What if I come from the other direction? What's it seem to be approaching? -4. So from that work, I can say, alright, we're going to come in first thing tomorrow. Have your notebooks out ready and we're going to straight into it. Sound good?
Tell me really cool. Alan Levitt of the Gulf. This deep. How did you make them back?
Well, you can put in functions. And so at the end, x squared so put in whatever function is in your limit.
Let's see, how much?
Second window. Good, you have asked. And the second
How mad would you be if I had a page 2.5 in my notes?
I'd be annoyed, but just don't do it again.
Yeah, well, I forgot my notebook in my locker.
Oh, killer. Hi guys.